Long before Pangaea, an ancient landmass called Kenorland stretched across Earth's surface, reshaping oceans, volcanoes, and even the air itself. Many geologists now think this forgotten supercontinent helped drive the planet into a deep freeze, locking Earth in ice from pole to pole. Today we explore how shifting plates, rising mountains, and changing chemistry may have turned Kenorland into the trigger for a global ice age. If you enjoy quiet journeys through deep time, please like, subscribe and share, and tell us in the comments what would you ask about a supercontinent that can freeze an entire world. Thank you for watching. Now let's begin. In the late Archean and earliest Paleoproterozoic Earth travels around a younger sun that shines less brightly than it does in later ages, yet still dominates the flow of energy that reaches the planet. The sun's total power output, called its luminosity, is lower than in more recent geological times, with many studies indicating that it stands at only about 70 to 80% of the value that characterizes the later Precambrian and Phanerozoic. So every square meter of Earth's surface receives less incoming solar energy than it does today. The planet orbits at roughly the same distance as in later eras, close to 150 million kilometers from the Sun, and the orbit is nearly circular, so the amount of light arriving at the top of the atmosphere varies only slightly over the course of a year. From a distant view in space, the young Earth and its star form a simple radiative system. Sunlight streams outward from the stellar surface. A small fraction of that light intercepts the planetary disk and Earth, in turn emits heat back into space as long wavelength radiation. This balance between incoming solar energy and outgoing heat sets the boundary conditions that make any climate on Earth possible during this distant time. The faint sun provides less energy, so if all other properties of the planet remain fixed, global temperatures tend to be lower than under a brighter star. However, even in this early interval, Earth is not a bare rock. It is wrapped in an atmosphere and covered in extensive oceans that both intercept and redistribute energy. The incoming sunlight first meets the upper layers of the atmosphere where gases, clouds, and any aerosols can absorb or scatter part of the radiation. Some wavelengths are reflected back into space before they can warm the surface, especially those that encounter bright cloud tops or particles suspended high in the air. The fraction of incoming light that is reflected is called the planetary albedo, and together with the sun's brightness, it strongly influences how much energy is actually absorbed by the Earth system. A high albedo means that a large share of incoming light is turned away, while a low albedo means that more energy enters the climate system and warms the surface and lower atmosphere. In the late Archean and earliest Paleoproterozoic, the exact value of Earth's albedo is not known in detail because clouds, ice cover, and atmospheric composition leave only indirect traces in the rock record. Researchers instead infer plausible ranges based on models of atmospheric chemistry, likely cloud properties, and the limited geological evidence for ice and reflective surfaces at different times. Within these bounds, a somewhat lower or higher albedo can help offset or amplify the faint young sun, either cooling or warming the planet. Once sunlight passes through the atmosphere and reaches the surface, it interacts with water and rock in different ways. Darker ocean water absorbs most of the visible light that enters it, converting that energy into heat that can be mixed downward by currents and waves. Exposed land where present may reflect more light if it is covered by bright minerals or shallow water, or may absorb more if it hosts darker volcanic rocks or soil. The distribution of oceans and land is not yet important at the scale of this section, because the focus remains on the overall energy exchange between the star and the planet, but the combined reflectivity of all surfaces contributes to the effective albedo. After absorbing solar energy, Earth must lose heat to maintain a long-term balance. The planet emits radiation at longer wavelengths, often described as thermal or infrared, which escape to space if they are not absorbed by gases in the atmosphere. At a basic level, the average surface temperature adjusts until the outgoing thermal radiation balances the absorbed solar input. With a fainter sun, the simplest energy balance would tend to place Earth near or below the freezing point of water, but the presence of atmospheric gases that absorb outgoing heat, especially greenhouse gases, and the dynamic behavior of clouds can shift this balance significantly. Even without specifying the exact mixture of gases, it is clear that the atmosphere plays a central role in regulating climate by controlling how easily heat can escape to space. Clues to the actual balance come from ancient sedimentary rocks, which often require stable bodies of liquid water to form. Layers of chemical sediments and shallow water deposits in Archean and earliest Paleoproterozoic successions indicate that oceans remain at least partly unfrozen, which means that the combined effects of greenhouse gases, clouds, and surface properties successfully keep average temperatures above the point where the planet would freeze solid under the faint sun. Because these records are incomplete and later deformation may disturb them, they do not yield a single precise climate solution, but they provide broad limits that any model of the early energy budget must respect. The rotation of the planet also influences how solar energy is distributed. During the late Archean and earliest Paleoproterozoic tidal interactions with the Moon have not yet slowed Earth's spin to its later rate, so a day is likely shorter than the 24 hours familiar from more recent times. Shorter days mean that any given point on the surface spends less time under direct sunlight and less time in darkness during each rotation, but the total energy received over many rotations remains determined mainly by latitude and season, rather than by the length of a single day. The faster spin may affect atmospheric circulation patterns and the detailed transport of heat, but at the level of the global energy budget, the key factors remain solar luminosity, orbital distance, and planetary albedo. Over spans of hundreds of millions of years, slow changes in the sun's brightness, subtle variations in Earth's orbit, and long-term shifts in atmospheric composition and surface reflectivity together shape the range of climates that are physically possible. In this young interval, with the sun still faint and the planet's basic radiative properties already in operation, Earth resides in a regime where relatively small changes in greenhouse gas concentrations or surface reflectivity can make the difference between a world with extensive liquid water and one dominated by ice. Earth's path around the sun, the angle of its spin axis, and the length of its day together control how sunlight is distributed across the surface in space and time during the late Archean and earliest Paleoproterozoic. The planet follows an orbit that is close to circular, so its distance from the sun varies only modestly over the course of a year. This means that the total solar energy arriving at the top of the atmosphere is set mainly by the average distance, which is similar to that of later ages rather than by strong swings between a close approach and a far point. At any moment, a narrow beam of sunlight intersects Earth's spherical surface at different angles depending on latitude. Near the equator, sunlight meets the surface more directly, spreading its energy over a smaller area and heating more efficiently. Toward the poles, the same beam is spread over a larger area and passes through a longer path in the atmosphere, so less energy reaches each square meter of ground or ocean. This geometric effect is already fully present in the late Archean and earliest Paleoproterozoic, and ensures that the tropics receive more average solar energy than the high latitudes, regardless of the exact details of the climate system. The tilt of Earth's axis, called its obliquity, adds a seasonal rhythm to this basic pattern. Obliquity is the angle between the planet's spin axis and the line that is perpendicular to the orbital plane. When this angle is non-zero, one hemisphere leans toward the sun during one part of the year and away from it during another part. As a result, each hemisphere experiences a cycle of seasons in which day length and the height of the sun in the sky change in a regular way. In the present day, obliquity is about 23½ degrees, but for the late Archean and earliest Paleoproterozoic, the exact value is not directly recorded in rocks. Physical models of the long-term evolution of Earth's spin suggest that the tilt likely lies within a similar broad range, although modest shifts over time are possible. When obliquity is larger, seasonal contrast becomes stronger with warmer summers and colder winters at mid and high latitudes. When obliquity is smaller, seasonal contrasts weaken, and the difference between summer and winter temperatures is reduced. In every case, the annual average energy at a given latitude depends on both the tilt and the geometric distribution of sunlight over the sphere. The spin axis does not only tilt, its direction in space also changes slowly through a motion known as precession. Precession causes the axis to trace a broad circle over long timescales, so that the timing of the seasons shifts relative to any small departures of the orbit from a perfect circle. In later Earth history, combinations of eccentricity, obliquity, and precession cycles generate well-known patterns of changes in the distribution of sunlight over tens to hundreds of thousands of years. For the late Archean and earliest Paleoproterozoic, the same physical processes are present, although the exact periods and strengths of these cycles differ. Because the Moon is closer, Earth's spin is faster, and the gravitational interactions between bodies are slightly altered. The rock record from this ancient time is not detailed enough to recover a full sequence of such cycles, but the underlying mechanics still operate and modulate the way sunlight is delivered to different latitudes and seasons. Tidal interaction between Earth and the Moon gradually transfers angular momentum from the planet's rotation into the Moon's orbit. Over hundreds of millions of years, this process slows Earth's spin and lengthens the day. In the late Archean and earliest Paleoproterozoic, the day is shorter than in later eras. Estimates based on models of tidal evolution and on subtle signals in later sedimentary records suggest that the day length may be on the order of 18 hours rather than 24. A shorter day means that a point on the surface passes from daylight to darkness and back again more rapidly. The number of days in a year is therefore higher than in modern times, because the total time required to complete one orbit around the Sun is similar but is divided into more shorter rotations. While the total annual energy received at a given latitude is not strongly changed by the exact length of the day, the shorter day influences how quickly the surface warms during daylight and cools during nighttime, and how atmospheric circulation patterns respond to the daily cycle of heating. Climatic models of such a faster spinning Earth show that the strength and position of jets, trade winds, and storm tracks can shift, but those details lie beyond the basic orbital and rotational description. The key point at this level is that in the late Archean and earliest Paleoproterozoic, the planet turns more rapidly under a still faint sun, giving a different rhythm to the alternation of light and darkness than in later ages. Changes in Earth's orbit on longer timescales also influence climate. The eccentricity of the orbit, which describes how much it deviates from a perfect circle, can vary due to gravitational interactions with other planets. Even small changes in eccentricity alter the difference between the closest and farthest distances from the Sun during the year. When eccentricity is higher, the planet receives slightly more solar energy near its closest approach and less near its farthest point, introducing a modest asymmetry to the seasons. When eccentricity is lower, the orbit is closer to circular and seasonal differences due to distance alone are weaker. While the overall impact of these changes on the total annual energy is small, the combination of eccentricity with obliquity and precession modifies the seasonal and latitudinal pattern of solar input. For the late Archean and earliest Paleoproterozoic, the exact eccentricity history is not known in detail, but the same gravitational principles apply, so similar families of orbital variations are expected. Across these different motions, the geometry of Earth's orbit and spin defines a framework for climate. Latitude sets a baseline contrast between warm low latitudes and cooler high latitudes. Obliquity imposes seasons by changing the height of the sun and the length of the day through the year. Precession shifts the timing of seasons relative to the orbit. Eccentricity introduces small differences in Sun-Earth distance over the year. Day length sets the tempo of the daily heating and cooling cycle. In the late Archean and earliest Paleoproterozoic, all of these elements operate under a sun that is still dimmer than in later times. The resulting pattern of sunlight over the globe is the physical backdrop against which the atmosphere, oceans, and surface materials respond, circulate and exchange energy, long before any specific continent is assembled into a larger configuration. In the late Archean and earliest Paleoproterozoic, the flow of energy between sun, atmosphere, ocean, and rock depends strongly on the gases that fill the air. Greenhouse gases are components of the atmosphere that let most incoming sunlight pass through to the surface but absorb part of the outgoing heat radiation, making it harder for that heat to escape directly to space. The main greenhouse gases for this time are likely carbon dioxide, methane, and water vapor, with nitrogen acting as a background gas that sets pressure but does not strongly absorb infrared radiation by itself. In the absence of detailed direct measurements, researchers use models' isotopic signals and indirect rock-based clues to estimate the range of possible concentrations of these gases. The precise numbers remain uncertain, but they must be high enough that the combined greenhouse effect can keep large areas of the ocean in liquid form under a sun that is still less bright than in later ages. Volcanic outgassing is a major source of carbon dioxide and other gases. In the late Archean and earliest Paleoproterozoic, internal heat flow is higher than in later Earth history, so mantle convection and magma production are more vigorous. Mid-ocean ridges continually create new oceanic crust, while volcanic arcs above subduction zones release gases from descending slabs and mantle melts. Large volcanic provinces may also erupt onto the surface or the sea floor. Each of these processes delivers carbon dioxide, water vapor, and sulfur-bearing gases into the atmosphere. If carbon dioxide accumulates faster than it's removed by weathering and burial in sediments, its concentration in the air rises, increasing the greenhouse effect. At the same time, chemical reactions between rainwater air and exposed rock slowly remove carbon dioxide from the atmosphere. When carbon dioxide dissolves in rainwater, it forms a weak acid that reacts with silicate minerals in rocks, producing dissolved ions that rivers carry to the ocean. There, these ions can eventually become carbonate minerals that lock carbon into solid form on the sea floor. This long-term cycle, often called the silicate weathering feedback, links climate and tectonics, because the rate of weathering depends on temperature, rainfall, and the amount of fresh rock exposed. In the late Archean and earliest Paleoproterozoic, this cycle still operates, although the exact balance between outgassing and weathering is not known in detail. With a fainter sun, higher greenhouse gas levels are generally needed to maintain moderate temperatures, but if weathering rates or seafloor alteration are high, they can lower carbon dioxide and move the climate toward cooler conditions. Methane is another important greenhouse gas for this time. In an atmosphere with little free oxygen, methane can reach higher concentrations than in more oxygen-rich eras because it is not rapidly destroyed by reaction with oxygen and other oxidants. Microbial communities that produce methane, sometimes called methanogens, likely occupy many anoxic environments such as sediments and deeper water columns. They convert simple carbon-bearing compounds into methane that escapes to the water and then to the atmosphere. Methane is a powerful absorber of infrared radiation, so even moderate levels can have a strong warming effect. However, methane also interacts with sunlight and other gases. If methane concentrations become very high, photochemical reactions in the upper atmosphere can form hazes made of complex organic particles. These hazes can reflect part of the incoming sunlight back into space and cool the surface even as the greenhouse effect continues to operate. The net impact of methane on climate in the late Archean and earliest Paleoproterozoic is the result of a balance between its infrared absorption and the reflective properties of any haze it produces. Models that explore these possibilities indicate that several combinations of carbon dioxide, methane, nitrogen pressure, and cloud properties can yield surface temperatures that keep water at least partly liquid. Water vapour is also a key greenhouse gas. Its concentration depends mainly on temperature because warmer air can hold more water vapour before it condenses into clouds or rain. As the surface and lower atmosphere warm, evaporation from oceans increases, raising water vapour levels and strengthening the greenhouse effect. This acts as a positive feedback. A small initial warming from carbon dioxide or methane leads to higher water vapour content, which produces further warming. In cold conditions, the opposite occurs and the atmosphere holds less water vapour, reducing its greenhouse contribution. Cloud formation introduces additional complexity. Clouds can both cool and warm the climate. Bright cloud tops reflect incoming sunlight and increase planetary albedo, which cools the surface. At the same time, clouds absorb and re-emit infrared radiation from below, contributing to the greenhouse effect, especially for high, thin clouds that are cold at their tops. The overall impact of clouds in the late Archean and earliest Paleoproterozoic depends on their type, altitude, thickness, and coverage. Because there is no direct way to observe ancient clouds, their properties and climate models are chosen within reasonable physical ranges, and different assumptions can lead to somewhat warmer or cooler solutions for the same gas composition. Despite these uncertainties, the combined greenhouse effect of carbon dioxide, methane, water, vapour, and clouds under a nitrogen-dominated atmosphere provides a consistent explanation for how Earth can avoid a permanent deep freeze under a faint sun, while still leaving room for episodes of cooling and glaciation. At the level of the planetary energy budget, greenhouse gases act as regulators of heat loss, while orbital geometry and solar luminosity control the amount and pattern of heat gain. In the late Archean and earliest Paleoproterozoic, this balance sets the stage for the climates that occur before, during and after the interval, when large land masses later assemble into broader continental groupings. Geological evidence from ancient sediments such as chemical deposits that require liquid water and possible paleosol horizons gives broad limits on allowable combinations of greenhouse gases and surface temperatures, even though it does not fix exact values. Within those limits, small relative shifts in carbon dioxide, methane, or cloud properties can move the planet between warmer states with ice restricted to high latitudes and cooler states where ice can expand more widely, always under the same, slowly brightening but still relatively faint sun. Inside, the young Earth heat from its formation and from the decay of radioactive elements remains higher than in later ages, so the mantle is warmer and more mobile, and the crust above it is more actively reshaped. The mantle is the thick rocky layer between the metallic core and the thin outer crust. In this era it convects strongly, which means that hot mantle material rises in some regions, cools, and then sinks elsewhere in large slow-moving cells. At the surface, this motion is expressed as plate tectonics, a system in which the rigid outer shell called the lithosphere is broken into plates that move slowly over the softer mantle beneath. There is still debate about how far back modern-style plate tectonics extends, and whether early Earth experiences continuous plate motion or more episodic shifts. But many lines of evidence, including ancient subduction-related rocks and long belts of deformed crust, support the idea that some form of plate interaction is already active by the late Archean and earliest Paleoproterozoic. Plates meet and separate along large boundaries that control where new crust forms and where old crust is recycled. At mid-ocean, ridges' rising mantle partially melts to produce basaltic magma that cools to form new oceanic crust. Because internal heat flow is higher, These ridge systems may be more widespread or more vigorous than in later times, with higher average production of new seafloor. The newly formed crust is hot and buoyant, so ridge crests stand higher than older, colder oceanic plate farther away. As plates move away from ridges, the oceanic lithosphere cools, becomes denser, and eventually can sink back into the mantle at subduction zones. In subduction zones, one plate bends and descends beneath another, carrying cold water, rich crust into the mantle where it heats up, releases water, and promotes partial melting above the descending slab. This melting feeds volcanic arcs that rise as chains of volcanoes at the surface. In the late Archean and earliest Paleoproterozoic, such arcs contribute significantly to building up thicker, more buoyant continental crust from earlier, more mafic material. The crust can be broadly divided into dense, thin oceanic crust beneath the deep basins, and thicker, lighter continental crust that stands higher and forms land. Continental crust in this time often consists of ancient cores, sometimes called cratons, surrounded by younger belts of deformed and metamorphosed rocks that record collisions and accretion of smaller fragments. These cratons are relatively rigid blocks that can persist for billions of years, while younger belts around them record the ongoing assembly and rearrangement of the outer shell. Because heat flow is high, continental crust may be more weakly supported at depth, leading to broad plateaus and thickened regions where collisions and magmatic additions occur. The exact distribution of land and sea is not known in detail, but many reconstructions suggest a world with extensive ocean areas and numerous continental and island arcs, some of which are already merging into larger groupings. Plate tectonics is tightly linked to the long-term cycles of gases and elements that affect climate. Volcanism at ridges arcs and large volcanic provinces releases carbon dioxide, water vapor, and other gases from the mantle into the atmosphere and oceans. Subduction carries sediments, altered oceanic crust and water, back into the deep interior, where some material is stored and some is returned to the surface through later magmatism. On land, tectonic uplift raises new rock surfaces into zones where weathering can act. Uplifted regions expose fresh silicate minerals to rain and chemical breakdown, which over long timescales can remove carbon dioxide from the atmosphere and store carbon in marine sediments. In this way, the rate and style of plate motion influence both the sources and sinks of greenhouse gases. In the late Archean and earliest Paleoproterozoic, with more active tectonics and higher volcanic fluxes, both outgassing and weathering likely proceed at different average rates than in later eras, although the exact values remain uncertain. The strong heat flow also affects the thickness and strength of the lithosphere. A hotter mantle tends to produce a thinner, weaker lithosphere that can bend and break more easily, so subduction and rifting may occur in different patterns than in a cooler planet. Rifting is the process by which the crust stretches and thins, often forming long linear valleys that may later become new ocean basins. In these settings, faults create subsiding regions where sediments can accumulate to great thickness. Such sedimentary basins preserve records of the early oceans and atmospheres and store large volumes of water, carbon, and other elements in solid form. Over time, as these basins are buried and deformed, they are welded into the growing continents, carrying their chemical signatures with them. Beneath the mantle, the core also plays a role in the global system. The core is mostly iron alloy with a liquid outer part that convects and generates Earth's magnetic field. That field extends far into space and deflects much of the charged particle flow from the sun, often called the solar wind. By shielding the upper atmosphere from direct erosion by these particles, the magnetic field helps Earth retain its gases and water over long time scales. Evidence from ancient rocks suggests that a magnetic field is already present by the late Archean, although its exact strength and configuration are still being investigated. With a working magnetic shield, the atmosphere and oceans can persist and interact with the crust and mantle, without catastrophic loss to space, even under the more intense radiation environment of a younger sun. The global ocean above the tectonic plates participates in cycles that link the deep interior to the surface environment. But in this section, it is viewed mainly as a moving heat storing layer that responds to the shape of the basins and the positions of ridges and continental margins. As plates drift, seaways open and close and the pattern of currents adjusts. While the detailed circulation cannot be reconstructed for this distant period, the basic principle holds that the large-scale arrangement of continents, ridges and deep basins controls how warm surface waters and cold deep waters move, how nutrients are distributed and how heat is transported from low to high latitudes. In the late Archean and earliest Paleoproterozoic, the combination of a hot interior active plate boundaries, persistent mantle convection, and a shielding magnetic field sets up a dynamic whole Earth system. The outer shell may appear stable on human timescales, but over tens to hundreds of millions of years plates shift, collide and separate, building and rearranging landmasses, modifying ocean basins and continuously exchanging gases and materials between the interior, the surface, the atmosphere and the sea. This ongoing tectonic activity provides the physical and chemical framework within which the early atmosphere and global ocean develop their distinctive compositions in a world that is still dominated by low oxygen conditions. In the late Archean and earliest Paleoproterozoic, the air above Earth's surface is very different from the oxygen-rich atmosphere of later ages. Nitrogen likely makes up most of the atmospheric mass, with carbon dioxide, methane, water vapour, and other trace gases present in smaller but still important amounts. Free oxygen, meaning oxygen molecules not bound within other compounds, is either absent or present only at very low levels compared with later times. In such an atmosphere, many chemical reactions that require oxygen proceed very slowly, and elements like iron and sulfur cycle in reduced forms that are uncommon at the surface in more oxygenated eras. Evidence for this low oxygen state comes from several types of ancient rocks. Paleosols, which are ancient weathered horizons that formed in contact with the atmosphere, show patterns of iron and other elements that indicate that oxygen is scarce in the air during their formation. Certain sulfur-bearing minerals preserve isotopic signals that would be erased if free oxygen were abundant. These records suggest that for long stretches of the late Archean and earliest Paleoproterozoic, the atmosphere remains anoxic, a term that describes conditions without significant free oxygen. In an anoxic atmosphere, methane released by microbes and other processes can persist for longer times because it is not rapidly destroyed by reactions with oxygen. Methane and carbon dioxide together help maintain surface temperatures above the freezing point of water, despite the faint sun. At the same time, low oxygen levels mean that ultraviolet radiation from the sun penetrates more deeply into the upper atmosphere, where it can drive photochemical reactions among gases like methane, carbon dioxide, nitrogen and water vapour. These reactions can form complex organic molecules and hazes that may influence the amount of sunlight reaching the surface. The exact balance between greenhouse warming and any cooling due to reflective hazes is still an active area of research, and different models explore various combinations of gas abundances consistent with the limited rock record. Beneath this atmosphere, Earth's global ocean covers large areas of the surface and interacts continuously with the air above and the rocks below. The ocean in this era is also largely anoxic, especially at depth. In an anoxic ocean, dissolved iron in its reduced form remains stable in the water column. Rivers carry iron from weathering of rocks on land into the sea, and hydrothermal vents at mid-ocean ridges add additional iron and other metals. In a world without much free oxygen, this iron does not immediately oxidize and precipitate near the surface. Instead, it can accumulate to high concentrations, especially in deeper waters that are isolated from any limited oxygen sources near the surface. The presence of large amounts of dissolved iron is recorded later in banded iron formations. A banded iron formation is a type of sedimentary rock made of alternating layers, rich in iron minerals and layers rich in silica, often deposited on the sea floor. These layers form when conditions allow dissolved iron to be oxidized and precipitate as solid minerals, perhaps due to local production of oxygen, by photosynthetic microbes, or changes in the balance of chemical reactions and mixing. Over long timescales, these deposits record episodes when parts of the ocean shift between more reduced and more oxidized states. Their abundance in late Archean and earliest Paleoproterozoic sequences indicates that the ocean holds large iron inventories and that the global environment is only slowly moving toward higher oxygen levels. The structure of the ocean likely involves strong stratification, meaning that different layers have distinct chemical and physical properties. Surface waters in contact with the atmosphere can exchange gases and may host microbial communities that perform photosynthesis, using light to convert carbon-bearing compounds into organic matter, and in some cases releasing oxygen as a byproduct. If that oxygen is produced, it is quickly consumed by reactions with dissolved iron sulfides and other reduced substances in the water and at the sea floor. As a result, any oxygen-rich zone near the surface stays thin and local for a long time. Below this surface layer, deeper waters remain anoxic and may contain high levels of dissolved iron and reduced sulfur species. Circulation between these layers, controlled by temperature, salinity, and basin geometry, continually moves water masses and redistributes chemical constituents, but the overall pattern preserves a contrast between more reactive, possibly weakly oxygenated shallow zones and strongly reduced deep waters. Microbial life plays a central role in the atmosphere-ocean system of this era. Photosynthetic microbes, including early forms of cyanobacteria, inhabit shallow marine environments, tidal flats, and perhaps some freshwater settings. They use sunlight to drive the conversion of inorganic carbon into organic matter, and in the case of oxygenic photosynthesis, they release oxygen. At the same time, other microbes thrive in the absence of oxygen. Methanogens produce methane in sediments and in parts of the water column, where simple carbon compounds are available and oxygen is absent. Sulfate-reducing microbes, where sulfate is present, convert sulfate into sulfide while decomposing organic matter. Iron-reducing and iron-oxidizing microbes contribute to the transformations between dissolved and solid iron phases. Together, these microbial metabolisms build a complex network of biogeochemical cycles that link carbon, sulfur, iron, and other elements. The balance between sources and sinks of oxygen is key. Every molecule of oxygen released by photosynthesis can be consumed by oxidation of reduced minerals, gases, and organic matter. For long periods in the late Archean and earliest Paleoproterozoic, these sinks are large enough to prevent oxygen from building up to high levels in the atmosphere. Weathering of exposed volcanic and ultramafic rocks, volcanic gas emissions rich in reduced species, and the reduced state of the mantle all maintain strong demand for oxygen at the surface. Only when these sinks are sufficiently diminished, and when photosynthetic oxygen production becomes large enough over time, can free oxygen start to accumulate more broadly. The exact timing of these changes is still being refined, but many lines of evidence point to a gradual trend toward higher oxygen levels during the earliest Paleoproterozoic, later described in the context of the Great Oxidation Event. In the interval focused on here, the atmosphere and ocean are still dominated by reduced chemical states, and oxygen is a minor component. The chemistry of the early oceans also affects nutrient availability for life. Phosphorus, nitrogen, and trace metals such as iron, molybdenum, and copper are important for biological processes. In a reduced ocean, some of these elements may be more or less available than in later oxygenated seas. For example, iron is abundant in dissolved form, while some other metals may be trapped in minerals that settle to the seafloor. The spatial and temporal distribution of nutrients influences where microbial communities are most productive and how much organic carbon they can fix and export to depth. The burial of organic carbon in sediments removes reduced carbon from the system and leaves behind oxygen that could in principle accumulate. Thus, the efficiency of organic carbon burial in marine basins is another factor that controls long-term atmospheric composition. Across the whole planet, the early atmosphere and ocean form a coupled system that responds to inputs from volcanic outgassing, weathering of rocks and biological activity, while being constrained by the physical framework of solar energy and planetary rotation described in earlier sections. An anoxic or weakly oxygenated atmosphere works together with a largely anoxic, iron-rich ocean to maintain a climate in which liquid water persists and microbial ecosystems operate, yet free oxygen remains scarce. This state sets the chemical background into which later tectonic and environmental changes will introduce large, stable continental areas and eventually conditions that favour more widespread glaciation. By the late Archean, Earth's outer shell already includes several large stable continental cores that act as building blocks for later larger land masses. These cores are called cratons. A craton is a piece of thick old continental crust and underlying mantle that has survived major deformation for very long times. It tends to be mechanically strong and buoyant, so it stands higher than surrounding regions and forms the foundation of long-lived continents. In this era, multiple cratons with Archean ages exist across the globe, separated by wide ocean basins and mobile belts of younger, more deformed rocks. Later reconstructions of Kenorland draw on these cratons as its main components, but how exactly they are arranged relative to one another is still under discussion. One of the best studied examples is the Superior Craton, now part of the interior of North America. It contains very old rocks that are mostly between about 3 billion and 2.5 billion years in age. Its geology preserves thick sequences of volcanic rocks known as greenstone belts, and associated sedimentary layers all intruded by large volumes of granitic magmas. Greenstone belts are belts of metamorphosed volcanic and sedimentary rocks that record ancient ocean floor island arcs and related environments. Between and around these belts, the crust is made of felsic gneisses and granitoids that reflect long histories of crustal growth and reworking. The Superior Craton shows evidence for multiple phases of deformation and magmatism, including long linear belts that many researchers interpret as ancient collision zones, where earlier microcontinents and arcs were welded together. Its size, internal structure, and late Archean stabilization make it a prime candidate for a central element of a larger continental assembly in this time window. To the northeast in present day, Eurasia, the Kola and Karelia regions, often grouped within a broader Fennoscandian shield, contain another set of old crustal blocks. These areas host Archean gneisses, greenstone belts, and late Archean to Paleoproterozoic sedimentary and volcanic successions that record a complex evolution. Ages of magmatic events, deformation phases, and sedimentation in the Kola and Karelia blocks show similarities to those in the Superior region. In some reconstructions, these similarities, together with paleomagnetic data and matching tectonic trends, support placing parts of Fennoscandia close to the Superior Craton within a shared Neo-Archean continental grouping. Other models, however, emphasize differences and prefer to treat these regions as separate supercratons or as parts of distinct continental clusters that only later approach one another. In the southern hemisphere today, the Kapval Craton in southern Africa and the Pilbara Craton in Western Australia provide further examples of ancient continental cores. Each contains very old rocks, in some cases older than 3 billion years, with granite greenstone terrains and high-grade metamorphic complexes. Some studies propose that these two cratons are once united in an Archean landmass sometimes referred to as Valbara, which may predate or overlap with later configurations that involve Kenorland. Whether Valbara represents a separate earlier supercontinent, an early stage of a broader aggregation, or a structure that partially overlaps with Kenorland remains debated. The existence of such proposals shows that the history of Archean continents likely involves multiple cycles of assembly and breakup, and that the name Kenorland is applied to one particular configuration within this long sequence rather than to all early continental groupings. Other cratonic fragments, such as those now present in parts of modern Laurentia, Baltica, Siberia, India, and other regions, also carry late Archean crust and may have participated in the wider continental patterns of this time. Some researchers group subsets of these cratons into supercratons with names like Superia and Sclavia, which may correspond to different faces or subsets of what later is collectively labelled Kenorland. In this view, Kenorland is not a single rigid landmass whose exact outline is known, but a working term for a large Neo-Archean to earliest Paleo-Proterozoic continental arrangement that includes many but perhaps not all of the major Archean cratons. The evidence that links these cratons rests on several types of data. One key line of evidence is paleomagnetism. When certain rocks cool from a molten or heated state, or when fine magnetic minerals grow in sediments, they can acquire a remnant magnetization that records the direction and strength of Earth's magnetic field at that time and place. By measuring this magnetization in rocks of known age, geologists can estimate the latitude at which the rock formed and the orientation of the craton relative to the magnetic field. When paleomagnetic directions from different cratons of similar age are compared, they can sometimes be matched in ways that suggest proximity or specific relative positions. However, paleomagnetism has limits. It constrains latitude and orientation, but not absolute longitude, and later tectonic rotations or remagnetization events can complicate the signal. As a result, several paleogeographic models can fit the same set of data, leading to competing reconstructions of how the cratons are arranged in a potential Kenorland. Another line of evidence comes from matching geological features such as orogenic belts, dike swarms, and sedimentary basins. Orogenic belts are long zones of deformed rocks that record major collisions. If two cratons share belts with similar ages, rock types, and structural trends, they may once have been joined along a common boundary. Large igneous provinces and dike swarms, which are sets of parallel tabular intrusions that cut across older rocks, can also link cratons when their ages, compositions, and orientations match. In some Kenorland models, late Archean dike swarms in one craton align with similar features in another, suggesting that both lay within the same stress field during a major magmatic event. Shared sedimentary successions, such as similar packages of shallow marine sediments or rift-related deposits, can further support links between cratons if they show matching age ranges and depositional histories. Even with these tools, the picture remains incomplete. Many Archean and earliest Paleoproterozoic rocks are deeply eroded, metamorphosed, or buried beneath younger cover, and gaps in exposure limit the ability to trace belts and structures continuously across craton edges. Radiometric age dating provides time constraints but always carries uncertainties. Different interpretations of how to group and correlate features can lead to different maps of how Kenorland is assembled. Some reconstructions depict a large coherent supercontinent by late Neo-Archean time with the superior Cola Karelia and other cratons forming a central core and additional blocks attached around the margins. Other reconstructions favour a more fragmented picture, with several loosely connected supercratons separated by wide oceans. What is generally agreed is that by the end of the Archean continental crust covers a larger fraction of Earth's surface than it did earlier, and that several large, relatively stable cratons exist that can participate in later assembly into bigger structures. In this state, Earth presents a surface with deep global oceans, interrupted by multiple broad continental platforms and island arcs. Some of these cratons already share boundaries where earlier collisions have created mountain belts and thickened crust. Others still drift in wide oceans with subduction zones consuming intervening seafloor. Over tens of millions of years, relative motions between these cratons bring some of them together along new convergence zones where further deformation and magmatism will eventually weld them into more extensive landmasses. It is within this framework of scattered but maturing Archean cratons, linked by uncertain but increasingly constrained geological and paleomagnetic ties, that the assembly of Kenorland takes shape in the late Archean and earliest Paleoproterozoic. In the Neo-Archean, relative motions between the major cratons begin to close the oceans that separate them and set the stage for the assembly of a larger continental mass, commonly grouped under the name Kenorland. Plate boundaries around these cratons host long-lived subduction zones where oceanic lithosphere sinks back into the mantle. As subduction continues, ocean basins' narrow arcs grow, and pieces of crust that once lie far apart are brought into contact. Over tens of millions of years, repeated episodes of convergence, magmatism, and deformation build broad belts of thickened crust along the edges of the cratons. These belts record orogenies, which are mountain-building episodes that occur when plates collide, compress, and stack slices of crust on top of one another. In the superior craton late Archean orogenic belts run for thousands of kilometers and contain rocks that are buried to deep crustal levels and later exhumed. Their ages cluster around the final stages of Archean time, and many reconstructions interpret them as sutures where smaller continental blocks, arcs, and microcontinents have fused into a larger coherent entity. Similar late Archean to earliest Paleoproterozoic belts occur along the margins of the Kola and Karelia blocks in Fennoscandia, and in other cratons, suggesting that these regions also experience collisional events during this interval. The pattern of ages and structures points to a period when many cratons undergo significant assembly and stabilization, although the exact way they fit together in space remains debated. Subduction zones around the edges of these cratons are not simple straight boundaries. They can step and curve, and their polarity, meaning which plate subducts beneath the other, can change over time. Island arcs, which are chains of volcanoes built on oceanic or thin continental crust above subduction zones, may collide with a craton margin, pause briefly as part of the craton, and then become involved in further collisions on the opposite side. Each collision adds another slice of crust, causing thickening and creating high-standing regions supported by deep crustal roots. Metamorphism, the transformation of rocks under heat and pressure, alters the minerals and textures of the crust in these zones. Partial melting produces granitic magmas that intrude the thickened crust, adding buoyant material and contributing to the growth of stable continental lithosphere. Over time, these processes convert formerly narrow arcs and fragments into wide continental platforms. In many Kenorland-style reconstructions, the late Archean superior region forms the core of such a platform. Around it, other cratons or supercratons approach along convergent margins. Some models place the Kola and Karelia units to the northeast of Superior, joined along belts that show similar ages of magmatism and deformation. Others position additional Archean blocks, such as parts of what later becomes Baltica or other shields along different flanks. In each case, the idea is that by the very end of the Archean, a large grouping of continental crust exists that is substantially larger than any individual craton and that contains multiple previously separate cores welded together. In alternative reconstructions, the assembly is more distributed, and the term Kenorland is reserved for one of several large continental clusters that occupy Earth's surface at roughly the same time. These alternative patterns again draw on the same basic features such as orogenic belts and magmatic ages, but interpret them as recording several supercretons rather than a single continuous supercontinent. The shared point is that this interval is a time of widespread crustal growth and welding. Large regions of continental lithosphere become mechanically stronger as thickened roots cool and stiffen, and the rate of new stabilization of Archean crust declines after this phase. The mechanics of plate interactions during Kenorland assembly also influence the internal structure of the resulting landmass. Where convergence is strong and prolonged deep roots of high-grade metamorphic rocks form, giving rise to future shields. Where convergence is oblique, meaning that plates slide past as well as collide, long strike-slip shear zones can dissect the crust and offset older structures. Back-arc basins can open behind arcs and then close again, trapping fragments of oceanic and arc crust within the growing continent. These internal sutures and fragments later act as zones of weakness, along which the continent may eventually rift or break when tectonic forces again pull the lithosphere apart. In the late Archean and earliest Paleoproterozoic, however, the dominant pattern in many regions is one of assembly rather than breakup. Craton margins that previously face open oceans now border collisional belts or newly attached fragments. Volcanic arcs that once stand as isolated chains above subduction zones now sit inland as belts of deformed rocks. Sedimentary basins that once lie along passive margins may be squeezed, folded, and uplifted. The resulting composite continent shows a mosaic of rock units of different ages and origins, stitched together by zones of deformation and intruded by younger granitic bodies. Within this mosaic, the core areas of old cratons preserve relative stability and record earlier Archean histories, while the surrounding belts document the late Archean to earliest Paleoproterozoic assembly events that bring these cores into closer proximity. On the scale of the whole planet, the assembly of Kenorland-style landmasses means that a significant share of Earth's buoyant crust now resides in one or a few large clusters rather than being spread among many smaller separate continents. This concentration modifies the distribution of lithospheric thickness, the locations of major plate boundaries, and the pattern of long continental margins that separate land from deep ocean. It lengthens some subduction zones while shortening others, and localizes large zones of uplifted terrain above areas of thickened crust. In this assembled state, long inland plateaus, broad shallow continental shelves and extensive interior regions of thick crust are present even if their precise shapes and positions on the globe cannot yet be fixed from the available geological and paleomagnetic record. In the late Archean and earliest Paleoproterozoic, the landmass that researchers call Kenorland is not observed directly, but is reconstructed from scattered fragments of ancient crust and from physical signals locked into rocks. Kenorland is usually described as a supercontinent, meaning a large aggregation of continental crust that gathers many of the major cratons of the time into one broad cluster. Because plate motions since that era have rearranged and broken apart the original configuration, the shape and position of Kenorland on the globe are inferred rather than seen. The main tools for this inference are paleomagnetic measurements, correlations of geological belts, and comparisons of sedimentary and magmatic histories across cratons. Each line of evidence gives part of the picture, and together they suggest that a substantial continental assembly exists by the end of the Archean, even though its exact outline and latitude remain uncertain. Paleomagnetism plays a central role in these reconstructions. When volcanic rocks cool from a molten state, or when some sedimentary rocks form tiny magnetic minerals inside them, align with Earth's magnetic field. Once the rock is locked, this remanent magnetization can preserve the field direction at the time of formation. By sampling rocks of known age across a craton and measuring their magnetization, geologists can estimate the ancient latitude of that craton and how it is oriented relative to the geographic poles. When these data are compiled for many ages, they trace an apparent path of the pole relative to the craton called an apparent polar wander path. If two cratons show similar paths over the same time interval rotated into appropriate positions, It suggests that they were once joined or lay close together in a single larger landmass. In the case of Kenorland, paleomagnetic data from the Superior Craton and from parts of Fennoscandia, such as the Kola and Karelia regions, have been used to argue for configurations in which these blocks share common latitudes and orientations during parts of the Neo-Archean and earliest Paleoproterozoic. However, paleomagnetic data from such ancient rocks carry uncertainties. Heating deformation or chemical changes can partially reset or overprint the original magnetization. Some rock units do not yield stable or well-resolved directions. Even when reliable directions are obtained, paleomagnetism constrains latitude and orientation, but not absolute longitude, so several different relative positions on the globe can fit the same data. As a result, multiple Kenorland reconstructions exist in the literature, all consistent with the available paleomagnetic information, but differing in the detailed arrangement of cratons. Geological matching provides a second major line of evidence for Kenorland's configuration. Late Archean orogenic belts, dike swarms, sedimentary basins, and magmatic provinces that cut or overlap the craton boundaries can sometimes be linked across present-day continents. For example, a belt of deformed rocks of a given age and character on one craton may line up with a similar belt on another, suggesting that they were once contiguous. Large igneous provinces or swarms of mafic dikes of similar age and orientation can imply that the cratons they cross experience the same tectonic stresses and magmatic events at the same time. In some Kenorland models, such features tie the superior region to parts of Fennoscandia and to other Archean blocks, forming long continuous belts that once ran across a larger composite continent. Shared successions of shallow marine sediments with comparable ages and depositional patterns add further support, in some cases hinting at broad continental shelves that rim a common landmass rather than separate small continents. From these data, a general picture emerges of Kenorland as a wide, multi-cratonic continent, with internal mountain belts, stable central shields, and surrounding passive margins that grade into deep oceans. Some reconstructions place much of Kenorland at low to mid-latitudes, with parts straddling the equator based on the paleomagnetic inclinations recorded in Neo-Archean rocks. Others allow for configurations in which substantial portions occupy mid to higher latitudes. In each case, the proposed positions reflect the latitude ranges implied by the magnetic data, together with reasonable assumptions about how a large continent might be arranged relative to the spin axis. The exact latitude band that Kenorland occupies at any given moment is still being refined, and it may shift with time as the continent drifts under the influence of plate motions. What remains robust is that by the latest Archean, a significant fraction of Earth's continental crust is clustered into one or a few large groups, and that Kenorland is one of these major groupings. The external outline of Kenorland in map view is also reconstructed only in broad terms. Many models show an irregular perimeter marked by long continental margins and embayments. Some edges likely face wide-open oceans where subduction consumes oceanic lithosphere, while other segments border narrow seaways or interior basins where rifting and extension thin the crust. Within the continent, ancient sutures where cratons collide and weld together run as internal mountain belts. Between these belts, older shield areas made of strongly metamorphosed and stabilized crust form relatively low-relief interiors over long timescales. These interiors stand above surrounding ocean basins, but may also host broad shallow depressions that fill with sediments as the thick crust cools and slowly subsides. The thickness of the continental lithosphere beneath Kenorland is not directly known, but is inferred to be substantial in core regions where repeated collisions and magmatic additions have built thick roots. These roots help maintain high standing areas and influence how the continent responds to later tectonic forces. In contrast, zones that have recently experienced extension or magmatic underplating may have thinner or more thermally softened lithosphere, making them more responsive to later rifting. Because only fragments of Kenorland are preserved today, and because later tectonic events have overprinted many of its features, all reconstructions carry significant uncertainty. Erosion has removed large volumes of rock, younger sediments bury key boundaries, and younger orogenies reuse older zones of weakness, obscuring the original patterns. Some regions that may once have been attached to the Kenorland assembly are now difficult to assign confidently, because their Archean records are sparse or heavily reworked. For these reasons, scientists often present several alternative maps of Kenorland, each consistent with a different weighting of paleomagnetic, geological and geochronological data. Rather than representing a final fixed picture, the current reconstructions are best viewed as working models that outline the scale of the supercontinent and identify the main cratonic pieces likely involved. Within this framework, Kenorland is understood as a large composite landmass that brings together multiple Archean cratons, includes extensive internal plateaus and mountain belts, and is surrounded by broad ocean basins whose exact shapes and positions are still under study. Its configuration forms the continental background for the atmosphere-ocean and tectonic interactions of the earliest Paleoproterozoic. During the lifetime of Kenorland, the composition of Earth's atmosphere does not remain fixed in the strongly anoxic state that characterizes much of the late Archean. Instead, over tens to hundreds of millions of years, in the earliest Paleoproterozoic, free oxygen in the air begins to rise from extremely low values toward levels that, while still far below those of later times, are large enough to change surface chemistry, ocean structure, and climate. This long transition is later grouped under the term Great Oxidation Event, which describes a drawn-out interval rather than a single moment. The underlying processes involve a balance between biological production of oxygen, chemical, and geological sinks that consume it, and the way continents and oceans around Kenorland influence both sides of this balance. Oxygenic photosynthesis is the main long-term source of free oxygen. In oxygenic photosynthesis, microbes use light to split water and fix carbon-releasing oxygen as a byproduct. Early forms of cyanobacteria are thought to carry out this metabolism in shallow marine and coastal environments, including broad tidal flats and platforms along the edges of continental blocks. Rock structures called stromatolites, which are layered build-ups formed by microbial communities, and trapped sediment become more common in some late Archean and earliest Paleoproterozoic successions, and are often interpreted as evidence for active photosynthetic mats. As Kenorland brings together large cratonic areas, extensive shallow seas, and continental shelves may fringe its margins. These wide, sunlit marine platforms provide suitable settings for microbial mats and plankton to intercept light and drive photosynthesis over large areas. In such places, oxygen can accumulate locally in the water column above the communities and in the thin layer of air directly in contact with the sea surface. However, for long stretches of time, any oxygen produced in this way is rapidly consumed by sinks. Reduced volcanic gases such as hydrogen and sulfur bearing species react with oxygen. Weathering of exposed rocks on land, especially those containing iron and other reduced minerals, also consumes oxygen as these minerals oxidize. In the ocean, dissolved ferrous iron and reduced sulfur species take up oxygen and form solid minerals that settle to the seafloor. Organic matter produced by photosynthesis is largely broken down again by respiration and decay, which use up oxygen or other oxidants and return carbon dioxide to the system. As long as these sinks match or exceed the rate at which photosynthesis supplies oxygen, the atmosphere as a whole remains effectively anoxic, even if small oxygen-rich microenvironments exist. For oxygen to rise more broadly in the atmosphere, the net input from photosynthesis must over long intervals exceed the combined sinks. One way to achieve this is to enhance the burial of organic carbon in sediments so that not all of it is reoxidized. When organic matter is buried and preserved in marine or coastal basins, the oxygen originally released during its formation is not immediately consumed by its decay. Tectonic changes associated with Kenorland may influence this burial. As the supercontinent assembles and later begins to rift and sag in places, new sedimentary basins form on its margins and in its interior. Some of these basins are restricted and prone to anoxic bottom waters, which can favour the preservation of organic rich muds. Uplift and erosion of highlands created during collision supply sediments and nutrients to the surrounding seas. Nutrient delivery, particularly of phosphorus and certain trace metals, can stimulate higher primary productivity in surface waters, increasing the amount of organic carbon available for burial. However, the exact links between continental arrangement nutrient supply productivity and organic carbon burial remain an open research topic. Different models assign different weights to each factor, and the rock record of this time is incomplete. It is therefore more accurate to say that Kenorland-era tectonics provide a range of conditions that may support enhanced carbon burial, rather than to claim a simple direct cause. Evidence for rising oxygen comes from several kinds of geological observations. In very old sedimentary rocks, some sulfur-bearing minerals show a pattern of isotopes that reflects photochemical processes in an oxygen-poor atmosphere. At some point in the earliest Paleoproterozoic, this pattern disappears from the record, consistent with a shift to higher oxygen levels that alters how sulfur cycles in the atmosphere and ocean. Certain minerals that are unstable in the presence of oxygen, such as detrital pyrite and uraninite, are common in river and delta deposits before this change, and become rare afterward, suggesting that oxygen in rivers and soils becomes high enough to oxidize these minerals before they can be transported far. Later Paleoproterozoic red beds, which are sedimentary rocks with iron oxide coatings that form in oxygenated settings, also indicate more widespread atmospheric oxygen. These signals do not pinpoint exact oxygen concentrations, but they show that the surface environment moves from a state where free oxygen is negligible to one where it becomes a persistent, though still modest, component of the air. As oxygen rises, it affects other gases. Methane is particularly sensitive. In an anoxic atmosphere, methane produced by microbes and other processes can accumulate to high levels because it is not quickly destroyed. In an atmosphere with more oxygen, methane reacts more rapidly and its lifetime shortens. As oxygen builds up to even a small fraction of modern values, the steady-state methane concentration is expected to fall. Since methane is a strong greenhouse gas, a decline in its abundance tends to cool the planet, all else being equal. Carbon dioxide levels may also evolve as weathering patterns change under new atmospheric chemistry, and as volcanic and metamorphic sources vary. Together, these changes in greenhouse gases alter the balance between incoming solar energy and outgoing heat, modifying the climate that surrounds Kenorland and the global ocean. How large and how rapid these changes are and how directly they connect to any specific climatic event are still under study. Some researchers emphasize the possibility that methane decline under rising oxygen could shift Earth from a relatively warm state into cooler conditions, while others highlight the roles of carbon dioxide drawdown, tectonic reorganization, and solar evolution. The available data do not yet allow a single simple explanation, so the role of Kenorland and its atmospheric changes in setting climate is treated as a set of linked but complex processes rather than as a single trigger. In the oceans around Kenorland, the rise of oxygen affects the redox structure of the water column. Surface waters in contact with the air become more oxygenated, at least along well-lit ventilated margins. Deeper waters may remain anoxic and rich in dissolved iron for long periods, especially in basins with restricted circulation. At the boundary between these layers, changes in mixing and oxygen supply can influence when and where iron precipitates to form banded iron formations. Some Paleoproterozoic iron formations have been linked to fluctuating oxygen levels and to pulses of oxidation that sweep through parts of the ocean. Again, the details are debated, but the overall picture is one of a stratified ocean where oxygenated surface layers expand and contract above a chemically reduced interior. As Kenorland persists and begins to evolve, the atmosphere above it slowly shifts from an almost fully reducing state to one in which free oxygen is a stable, though still minor component. This shift alters chemical weathering on land-ocean nutrient cycles and greenhouse gas inventories. It does so over long spans of time through many incremental changes rather than through a single step. Within this changing atmospheric and oceanic framework, the assembled supercontinent interacts with winds, moisture and currents to produce characteristic patterns of climate and surface conditions that reflect both its size and its evolving environmental background. When a large share of Earth's continental crust gathers into Kenorland, the pattern of windstorms and surface environments adjust to the presence of a broad landmass that interrupts the global ocean. The exact shape and latitude of Kenorland are not fully fixed, but in most reconstructions it spans a wide range of latitudes and includes long coastlines, shallow shelves, and a substantial interior. Under the faint sun and an atmosphere that is still richer in greenhouse gases than later in Earth history, climate models for supercontinent configurations provide one of the main tools for thinking about its weather patterns. These models start from the orbital geometry and greenhouse background, already described, and then introduce a large continent into the atmosphere-ocean system. They consistently show that such a continent tends to develop strong contrast between coastal regions in the interior, and between low latitudes and higher latitudes, even when greenhouse gas levels differ from modern values. At low and mid latitudes along Kenorland's coasts, warm surface waters and moist air over nearby oceans supply humidity to the atmosphere. When prevailing winds blow on shore, this humid air rises over the continent, cools and releases precipitation. The result is broad belts of relatively wet climate near some coastal margins, especially where onshore winds dominate much of the year. If parts of Kenorland lie near the equator, these margins may host frequent convective storms driven by intense solar heating and abundant moisture. Where sections of the coast face cooler currents or lie under more stable atmospheric layers, they may be drier, but in general, ocean-adjacent regions have more direct access to moisture than the distant interior. Farther inland, the climate on Kenorland depends on distance from the sea elevation and large-scale wind patterns. As moist air masses travel across the continent, they lose water through repeated episodes of condensation and rainfall. By the time these air masses reach the inner parts of the continent, they may be much drier. In such regions, the combination of continentality, meaning large land areas, far from the moderating effect of the ocean, and possibly higher elevation promotes more extreme temperature ranges between day and night and between seasons. Summers can be warmer, because land heats quickly under strong sunlight, and winters can be cooler, because land also loses heat rapidly, especially under clear skies. If mountain belts rise along some internal sutures, or along Kenorland's margins, they further shape the pattern of rainfall. When moist air encounters a mountain range, it is forced upward and cools, enhancing precipitation on the windward side. On the leeward side, air descends, warms and dries, creating rain shadow effects where climates are more arid. The presence of such orographic patterns is consistent with the mosaic of collisional belts and highlands, inferred from the geological record of cratons that later form parts of Kenorland, although the exact positions and heights of these ranges are not known. In the atmosphere above, large-scale circulation responds to the distribution of land and sea. The equatorial region continues to host rising motion in belts, where warm air ascends while air sinks in subtropical zones on either side. These cells, together with the rotation of the planet, help establish prevailing easterly winds in the tropics and westerlies at mid-latitudes. Over a large continent, summer heating can drive monsoon-like systems in which air flows inland at low levels, rises over the hot land, and returns aloft, creating strong seasonal reversals of wind directions. The strength and exact pattern of any Kenorland monsoon circulations depend on its latitude size and the distribution of surrounding oceans, factors that remain partly unconstrained, but the basic physical tendency for large land masses to generate seasonal thermal contrasts with adjacent seas is robust. Storm tracks where mid-latitude cyclones commonly travel tend to follow the boundaries between warm and cold air masses and can be guided by the positions of jet streams. In configurations with a large supercontinent, these tracks may run along the oceanic flanks of the continent or cross parts of the landmass at preferred latitudes. Over time, this creates regions that experience more frequent storms and precipitation, and other regions that are more often under the influence of stable high-pressure systems with clearer, drier conditions. Surface environments on Kenorland reflect this climatic structure. Along active continental margins where subduction occurs, offshore coastlines may be rugged with uplands close to the sea and relatively narrow shelves. Here erosion delivers sediments rapidly to deep waters through canyon systems and submarine fans. Along more passive margins that face wide ocean basins without nearby subduction, broad continental shelves can develop covered by shallow epicontinental seas when global or regional sea levels are high. These seas host sedimentation in environments that range from shore-face sands and tidal flats to deeper shelf muds and carbonates. The character of these deposits encodes information about water depth, energy levels, and climate, but in the case of Kenorland, many of these records are later deformed and metamorphosed, so only parts of the original signals remain. Interior basins on Kenorland form when parts of the thickened continental lithosphere sag as they cool, or when stresses create gentle downwarps in the crust. Such basins can collect sediments over long periods, recording lake, river, and shallow marine environments that respond to local and regional climate. In moister interior regions, rivers may be perennial, and floodplains may support widespread fine-grained deposition. In more arid interiors, ephemeral streams, wind-blown sands, and playa-style lakes may dominate. The relative abundance of fluvial, aeolian, and lacustrine deposits in surviving rock successions offers indirect clues to past aridity and seasonality, although later tectonic overprinting often complicates these signals. Around Kenorland, the pattern of ocean currents is influenced by the positions of its margins and by the depth and geometry of surrounding basins. Where narrow seaways connect major ocean basins, strong currents may funnel through, promoting mixing between water masses. Where large embayments indent the continent, local circulation cells can develop with surface waters, warming and cooling according to season and latitude. Upwelling zones where deeper waters rise to the surface may occur along some wind-driven coastal regions, bringing nutrients that support higher biological productivity. The chemical structure of the ocean, with an oxygenated or weakly oxygenated surface layer above an anoxic interior, interacts with these currents. Well-ventilated shelves and coastal zones attached to Kenorland margins may host more oxygenated surface waters, while deeper basins and restricted arms of the ocean remain anoxic and iron-rich. Over time, this spatial pattern shapes where banded iron formations and other chemical sediments accumulate. Gradual changes in atmospheric composition, including the slow rise of oxygen and possible declines in methane and carbon dioxide, occur against this backdrop of supercontinent climate. These changes adjust global temperature ranges, humidity patterns, and the intensity of wind systems. Because Kenorland concentrates a large area of land in one region, any shift in global climate can lead to marked contrasts between its humid margins and its drier interiors, and between its low-latitude shelves and higher-latitude plateaus. The preserved sedimentary and metamorphic record from cratons that once formed part of Kenorland captures only a fraction of these environments, but together with physical climate models, it supports a picture of a world where a large composite continent shapes the paths of air and water, creating distinct belts of weather and surface conditions across its extent. As the earliest Paleoproterozoic unfolds, the climate around Kenorland and across the globe shifts from relatively warm conditions supported by strong greenhouse gases toward a state in which long-lived glaciations become possible. This transition does not happen in a single step. It is the result of gradual changes in atmospheric composition, tectonic forcing, and surface processes that interact with the faint but slowly brightening sun. The large land area of Kenorland plays a role in these changes through its effect on chemical weathering, sediment supply, and the burial of carbon, but the exact chain of cause and effect remains an active subject of research. The long-term carbon cycle provides one of the central controls on global temperature. Volcanic outgassing from mid-ocean ridges' subduction zones and large igneous provinces supplies carbon dioxide to the atmosphere. Weathering of silicate rocks on land, coupled with the burial of carbonate minerals and organic carbon in sediments, removes carbon dioxide over long timescales. On a planet with small scattered continents, the total area of exposed silicate rock available for weathering is limited. When a large supercontinent such as Kenorland is present, the area of land above sea level is greater, and many parts of that land may lie in climatic zones, with substantial rainfall and moderate temperatures. In such settings, rainwater and soil fluids can react more extensively with silicate minerals, drawing down carbon dioxide from the atmosphere. If the rate of weathering and burial of carbon exceeds the rate of volcanic supply for extended periods, atmospheric carbon dioxide gradually declines. With less carbon dioxide, the greenhouse effect weakens and global temperatures tend to fall. At the same time, the structure and chemistry of the atmosphere are evolving, because oxygen from oxygenic photosynthesis is slowly becoming more important. As oxygen rises from extremely low levels toward values that begin to affect surface environments, methane concentrations are expected to decrease. Methane is a strong greenhouse gas, and in an anoxic atmosphere it can accumulate to high levels. In a more oxygenated atmosphere, methane is destroyed more quickly by oxidation in the air, reducing its steady-state concentration. Models of atmospheric chemistry for the earliest Paleoproterozoic often find that even modest increases in oxygen lead to large drops in methane. This shift reduces the greenhouse warming contributed by methane and cools the climate. The exact balance between declining methane evolving carbon dioxide and water vapor feedbacks is not yet fully constrained, but most scenarios that combine a rising oxygen background with strong silicate weathering on extensive continents point toward cooler conditions than in the late Archean. The sun also slowly brightens as it ages, increasing its luminosity by a small amount over the hundreds of millions of years that separate the late Archean from the onset of major Paleoproterozoic glaciation. In simple energy balance terms, a brighter sun would tend to warm the planet, but if greenhouse gas concentrations decline sufficiently, the net effect can still be a move toward lower temperatures. In this sense, solar evolution sets a background trend while atmospheric composition and surface reflectivity control the detailed direction of climatic change. Geological evidence shows that during the earliest Paleoproterozoic, thick successions of sedimentary and volcanic rocks around the margins of some cratons record multiple glacial episodes. On the flank of the superior craton, for example, a long sequence of Paleoproterozoic strata includes diamictites and other deposits interpreted as glacial in origin, interbedded with non-glacial units. Similar age intervals with glacial features occur in parts of Fennoscandia and elsewhere. These deposits often grouped into what is called the Huronian glacial interval, and related successions suggest that Earth experiences several major glacial episodes, sometime between about 2,450,000,000 and 2,200,000,000 years ago. In many cases, these glacial units are overlain by chemical sediments, including carbonates, and in some settings banded iron formations, which point to complex changes in ocean chemistry before and after the glacial periods. The thickness and geographic spread of these glacial deposits indicate that ice is not confined to small high-latitude caps. Instead, ice-related sediments appear at paleolatitudes that may be relatively low, based on paleomagnetic constraints on the host rocks. This has led some researchers to propose that parts of the planet, and perhaps much of it, are covered by extensive ice sheets and sea ice during some of these events. Others interpret the data as consistent with large but more regionally distributed ice masses. The degree to which these glaciations approach a fully global snowball state remains debated, partly because the reconstructions of paleolatitude and the original extent of the deposits carry uncertainties. What is widely accepted is that the climate regime of the earliest Paleoproterozoic includes one or more intervals when ice extends far from polar regions and persists for long spans of time, representing an icehouse state on geological timescales. Ice-related feedbacks in the climate system help amplify the cooling. As ice sheets and sea ice expand, the planetary albedo increases because snow and ice reflect a large fraction of incoming sunlight. With more of the sun's energy reflected back to space, the surface and lower atmosphere receive less energy and cool, further allowing ice to spread even more. This ice albedo feedback operates alongside the greenhouse gas changes, reinforcing the transition from warmer to colder climates. The eventual extent of cooling depends on how far greenhouse gas concentrations fall, how clouds respond, and how efficiently the oceans redistribute heat. When the climate system remains in a cooler configuration for long intervals, the term icehouse is used to distinguish it from warmer greenhouse states. The timing of these Paleoproterozoic glaciations overlaps with evidence for changes in tectonic configuration and for the evolution of Kenorland. Some studies suggest that rifting and breakup of parts of Kenorland occur during or after the main glacial intervals as extensional tectonics opens new basins and seaways. Others place significant tectonic reorganizations slightly earlier. The correlation between supercontinent cycles and major climate shifts is an area of ongoing study. It is physically reasonable that the assembly and breakup of large continents influence climate through their control on weathering, volcanic outgassing, and ocean circulation, but the available data do not presently support a single simple statement that Kenorland alone triggers the icehouse. Instead, the transition is viewed as the outcome of several linked processes that include the rise of oxygen changes in methane and carbon dioxide, the presence of extensive land at certain latitudes, and the inherent feedbacks of the climate system under a faint but brightening sun. On the planetary scale, the result of these combined processes is that Earth moves from a late Archean world with relatively stable liquid oceans and no clear record of very widespread glaciation into an earliest Paleoproterozoic world, where thick, laterally extensive glacial deposits and related chemical sediments appear in several cratonic regions. Within this broad shift, Kenorland provides the main continental framework, hosting highland shelves and basins that respond to and record the cooling climate. In later sections, attention narrows from the global transition to the growth of ice sheets and sea ice on and around the supercontinent, and to the ways in which these ice masses interact with rock water and sediment to reshape the surface. As cooling strengthens in the earliest Paleoproterozoic conditions around Kenorland and across the globe, move into a regime where snow and ice can persist from year to year on land and on the sea. At first, this persistence is most likely to occur at high latitudes and at higher elevations where incoming solar energy is lower and the air is cooler. On uplands and plateaus within, and around the assembled continent, winter snowfall no longer melts completely during the warm season. Snow that survives the summer allows fresh snow in later years to accumulate on top of older layers. Under its own weight, this stack of snow compacts, expels air, and transitions into firn and then into glacial ice. Once this compacted ice body becomes thick enough, it begins to deform and flow slowly under gravity, marking the onset of true ice sheets and glaciers. As greenhouse gas levels decline and the planetary energy balance shifts further toward colder conditions, the zones where ice can persist expand. Regions that previously experienced seasonal snow now see that snow survive from one year to the next, and new sectors of Kenorland's uplands pass the threshold needed for glacial initiation. The geometry of the supercontinent influences the pattern of this growth. High interior plateaus, long ridges associated with ancient orogenic belts, and broad, gently sloping shields provide wide surfaces where ice can spread once it forms. Because land heats and cools more rapidly than ocean continental interiors, can reach low winter temperatures even when global mean temperature changes are moderate. Under a cooler overall climate, winters lengthen and summers weaken at many latitudes, increasing the fraction of each year when temperatures remain below freezing in these continental interiors. As a result, ice sheets on Kenorland tend to nucleate where elevation and latitude combine to favour cold conditions, and then extend outward toward lower ground. Once ice sheets reach sufficient thickness, their upper surfaces sit high in the atmosphere where air is generally colder. This elevation effect helps maintain low surface temperatures on the ice itself, reinforcing its stability. Snow that falls on the high interior parts of ice sheets adds to their mass, while at their margins ice flows outward and downward under its own weight. The flow rate depends on ice thickness, temperature, and the nature of the underlying bedrock and sediments. In some regions, basal ice may be cold and frozen to the substrate, with slow deformation concentrated within the ice column. In others, pressure melting and the presence of subglacial water may promote sliding, allowing the ice to move more rapidly over the underlying rock. At the scale of the whole supercontinent, this means that ice sheets develop broad domes in their accumulation zones and tongues or lobes, where they approach their margins, feeding outlet glaciers that carry ice toward lower elevations, and in some cases toward the sea. Around the edges of Kenorland and its rifted fragments, cooling also affects the adjacent oceans. When surface ocean water at high and mid-latitudes cools to the freezing point, sea ice begins to form. In calm conditions, small ice crystals and thin sheets develop and gradually coalesce into thicker flows. Wind and currents can then push these flows together into ridged pack ice. Sea ice acts as a barrier between the ocean and the atmosphere, reducing heat loss from the water and limiting direct exchange of gases and moisture. As climate cools further, the zone of seasonal sea ice expands equatorward, and areas that once only freeze in winter may remain ice-covered for longer parts of the year. In some reconstructions of Paleoproterozoic glaciation, geological and paleomagnetic evidence suggests that glacial deposits occur at relatively low paleolatitudes, implying that both land-based ice and sea ice may extend far from the poles. The extent to which sea ice reaches truly tropical latitudes, and whether the planet approaches a fully ice-covered state, remains uncertain and is the subject of continued study. Some models allow thick, long-lived sea ice in low-latitude oceans under strongly reduced greenhouse forcing, while others favour extensive but incomplete coverage. In every case, however, it is clear that ice plays an increasingly important role in shaping the surface conditions around Kenorland. The growth of ice sheets and sea ice changes the planetary albedo. Snow and ice reflect a large fraction of incoming sunlight compared with darker ocean water or vegetated land. As ice cover increases on both land and sea, the average reflectivity of Earth's surface rises. With more of the incoming solar radiation reflected back to space, less energy is available to warm the surface and lower atmosphere. This leads to further cooling and allows ice to spread still more, a process known as ice albedo feedback. Under conditions where greenhouse gases are already weakened, this feedback can be strong enough to maintain and deepen the icehouse state. The hydrological cycle also adjusts to the new climate. Colder air holds less water vapor, and lower sea surface temperatures reduce evaporation from the oceans. As a result, the total amount of precipitation may decrease in some regions. Where moisture supply remains adequate, snowfall over ice sheets continues supporting their growth and maintenance. In other areas, especially in the cold dry zones downwind of large ice masses, precipitation may be low. Their ice margins can stabilize when the outward flow of ice is balanced by the limited input of new snow. Wind erosion of exposed surfaces in dry glaciated regions can generate fine mineral dust that may be transported and deposited elsewhere, including on snow and ice surfaces, slightly darkening them and altering local melt rates. The presence of thick ice over large parts of Kenorland also affects the solid Earth. Ice sheets several kilometers thick exert significant pressure on the underlying crust, causing it to subside over long timescales. This subsidence creates depressions that can influence the pattern of ice flow and the location of peripheral bulges around the ice load. If ice extends onto continental shelves, its mass can depress those margins as well, modifying relative sea level at both local and regional scales. When ice volume changes, meltwater added to the oceans also affects global sea level, altering the depth of surrounding shelves and basins. During times of peak glaciation, sea level can fall relative to the continental surface, exposing wider areas of shelf around some parts of Kenorland, while other regions remain submerged or buried under grounded ice. In the atmosphere, the continued presence of extensive ice modifies temperature gradients between low and high latitudes. Stronger gradients can influence the positions and strengths of jet streams and storm tracks. Storm systems that form along the boundaries between cold air masses over ice and relatively warmer air over open ocean can drive strong winds and episodic snowfall along the margins of the ice sheets. Over interior ice surfaces, conditions may be more stable, with persistent cold temperatures, clear skies, and low precipitation. The overall effect is a climate system in which Kenorland's ice-covered regions form large cold thermal masses that interact with the surrounding atmosphere and ocean to create sharp contrast between icy and ice-free areas. Throughout this interval, volcanic outgassing continues from mid-ocean ridges, arcs and intraplate magmatism, supplying carbon dioxide and other gases to the atmosphere even as weathering and ice cover modulate their removal. The exact balance between sources and sinks of greenhouse gases during the peak of Paleoproterozoic glaciation is not known, and different models explore a range of possibilities consistent with geological constraints. What is clear is that the presence of a large ice-covered or partly ice-covered Kenorland is both a response to and a participant in the global climate system of this time. Its ice sheets and surrounding sea ice arise under cooler global conditions driven by changes in greenhouse gases and solar energy balance, and in turn they reinforce those conditions by altering reflectivity circulation and the hydrological cycle. In later stages of the icehouse, regional expressions of this glaciation manifest as specific patterns of ice erosion and deposition on and around the supercontinent, leaving physical records in the form of modified landscapes and sediments that persist long after the ice has gone. On the broad surface of Kenorland during its glaciated intervals, regional landscapes take on forms that reflect the interaction between thick ice flowing water and the underlying ancient crust. In highland areas and along long interior ridges built during earlier orogenes, ice accumulates to great thickness and moves downslope under gravity carving valleys and modifying pre-existing relief. Where older mountains and plateaus once rise above surrounding terrain, ice caps now cover them, feeding outlet glaciers that flow through weaker zones in the crust and along pre-existing river valleys. These glaciers erode their beds through a combination of abrasion, in which rocks frozen into the base of the ice scrape and polish the substrate, and plucking, in which blocks are lifted from fractured bedrock and carried away. Over time, these processes deepen and widen valleys, replacing sharp V-shaped river cuts with broader U-shaped glacial troughs. Cirques, which are bowl-shaped hollows at the heads of valleys, form where ice accumulates and over-deepens its source regions. Although many of these detailed landforms are later modified or obscured by subsequent metamorphism and erosion, their general styles are consistent with what is observed in younger glaciated terrains and with the mechanical behavior of ice on sloping rock surfaces. In interior basins that lie at lower elevations between highlands, ice behaves differently, where ice sheets spread out from their accumulation centres on plateaus and ridges. They can cover large lowland regions with relatively uniform slow-moving ice. The underlying bedrock in some of these areas may already be relatively flat and resistant, while in others it may consist of softer sedimentary or volcanic rocks that are more easily eroded. Under thick, slow-moving ice, stresses at the base are distributed across wide areas. Basal meltwater produced by pressure melting or by geothermal heat can collect in subglacial channels and cavities, lubricating the interface between ice and rock. This water can move in networks of tunnels and sheets beneath the ice, carrying fine sediment and sculpting streamlined features and soft deposits. In places, flow focuses into subglacial channels that incise into the bed, creating elongate depressions that can become lake basins when ice cover later thins. In other zones, ice may remain frozen to its bed, limiting erosion and leaving preglacial surfaces relatively intact. The resulting patchwork of strongly eroded and more weakly modified areas produces a complex landscape at the regional scale, with corridors of over-deepened valleys and basins separated by more subdued uplands. At the margins of interior ice masses where flow becomes more divergent and ice thins, the glacier surface develops crevasses and undulations that reflect underlying topography. Here the ice deposits till a mixture of clay, silt, sand, gravel and boulders that is released as the ice deforms and melts, till can accumulate beneath the ice on its surface and along its front. Where ice margins remain near a fixed position for extended periods, repeated deposition of till and other debris builds up morainic ridges that roughly trace former ice limits and positions of relative stability. These ridges consist of unsorted material carried by the ice and are later reshaped by meltwater and gravitational processes. In settings where ice advances and retreats repeatedly earlier, moraines may be overridden and partially destroyed, and new ridges may form farther outward or inward, recording a sequence of icefront positions. Such patterns allow in younger glacial systems the reconstruction of ice fluctuations. In the case of Kenorland age glaciations, only fragments of these records are preserved, but their presence in some Paleoproterozoic successions indicates that ice margins on and near the supercontinent can be dynamic over the duration of the glacial intervals. Proglacial environments, which are regions immediately in front of ice margins, develop a range of surface features controlled by meltwater and sediment load. During warmer seasons or under periods of enhanced basal melting, meltwater emerges from the ice in channels and distributary networks. These streams carry suspended sediment and coarse debris away from the ice front and deposit them as outwash fans and braided river plains. Deposits in these settings are typically well bedded and stratified with layers of sand and gravel laid down by shifting channels. In low-lying interior basins confined by topographic highs, meltwater can pond to form proglacial lakes. These lakes receive both detrital sediment from inflowing streams and ice-rafted debris from floating ice blocks that carve from the glacier front, where icebergs drift across lake surfaces and release their load of stones as they melt. Drop stones fall into fine-grained muds, producing characteristic textures in the sedimentary record. The water in proglacial lakes can be cold and turbid with seasonal variations in inflow and sediment delivery that create rhythmic layering such as varve-like couplets of silt and clay, although the exact expression in Kenorland age basins depends on local conditions that are only partly known. In some interior regions of Kenorland, glaciation may be less continuous or less intense. Topography, distance from moisture sources and latitude all influence whether ice persists over entire intervals or whether it advances and retreats in response to climatic fluctuations. Areas in range shadows behind major ice-covered uplands may receive low snowfall limiting ice thickness even under cold conditions. Other zones closer to moisture-laden winds may support thicker and more persistent ice cover. Paleoglacial indicators preserved on different cratons suggest that not all parts of the supercontinent experience identical glacial histories. Some cratonic margins and interiors show thick sequences of diamictites and associated glacial faces, while others record more limited ice-related deposits or emphasize non-glacial sedimentation during overlapping time windows. This spatial variability is consistent with a climate system in which the growth and decay of ice respond not only to global greenhouse gas levels, but also to regional circulation patterns and to the specific elevations and positions of land masses. Beneath the ice bedrock of Great Age records both older tectonic events and the imprint of glaciation. As ice moves over this substrate, it can polish and striate rock surfaces, leaving linear grooves and ridges that indicate former ice flow directions. It can also excavate basins into weaker or fractured zones, preferentially eroding along fault lines and lithological boundaries. Sediments eroded from these regions are transported within and beneath the ice and are redeposited downstream, creating thick accumulations in topographic lows. Over long timescales, repeated glacial cycles can lower regional surfaces and reduce relief, producing gently rolling shields dotted with low hills and basins. In some Paleo-Proterozoic terrains thought to be related to Kenorland or its fragments, glacial erosion surfaces capped by tillites and other deposits may represent such regionally smoothed landscapes, though subsequent metamorphism often makes detailed interpretation difficult. The presence of major ice masses on Kenorland also influences groundwater and hydrological regimes in the underlying crust. The weight of ice can pressurize pore waters in fractured rocks and sediments, driving fluid flow along permeable pathways. When the ice front retreats or thins, pressure releases can allow these fluids to migrate and interact with reactive minerals, altering their chemistry. In some cases, such processes may contribute to the formation or modification of ore deposits, particularly where metal-bearing fluids move through specific rock units. While the details of such mineralization in the Paleo-Proterozoic are the subject of specialized studies, the general link between glaciation fluid flow and crustal evolution forms part of the broader regional impact of ice on Kenorland's interior. Across the supercontinent, the combined result of these processes is a mosaic of glaciated highlands, modified interior basins and proglacial terrains, each recording aspects of ice dynamics and climate during the Paleo-Proterozoic icehouse. High plateaus and ridges host thick ice caps and valley glaciers that carve a braid and transport debris. Lowland interiors support expansive ice sheets with complex basal hydrology and variable erosional signatures. Proglacial lakes and outwash plains collect sediments and ice-rafted material that later lithify into stratified rocks containing drop stones and other glacial indicators. Together, these regional scale features build the physical record of how ice occupies and reshapes the interior parts of Kenorland during its extended early Paleo-Proterozoic glaciations. Along the outer edges of Kenorland and its rifted fragments during Paleo-Proterozoic glaciation, The contact zone between land ice and ocean forms a set of regional environments that differ from the glaciated interiors but remain strongly shaped by cold climate. Continental margins facing deep oceans or broad marginal seas host marine terminating glaciers and ice sheets that deliver ice directly to the water. Where thick ice from inland plateaus flows down major valleys to the coast, it can carve deep troughs that extend below sea level. When sea level is high enough, these troughs become fjord-like inlets with steep rock walls and over-deepened basins. Ice moving through them may ground along the floor inland but float as it approaches deeper water, forming ice shelves that are still attached to the inland ice, but lie mostly afloat. Calving at the seaward edge of such ice shelves, and at the fronts of tidewater glaciers, releases icebergs into the surrounding ocean. These icebergs, carrying rocks and sediments entrained in the ice, drift away under the influence of currents and winds. As they melt, they drop their loads into the water column and onto the sea floor, creating scattered clasts known as ice-rafted debris within otherwise finer-grained marine sediments. The distribution of such debris over continental shelves and deeper basins is one of the key signatures of glaciation in marine successions of Kenorland age. On continental shelves surrounding the supercontinent, the thickness of ice cover varies. In some regions, ice advances across the shelf and grounds to the shelf edge, eroding the substrate and depositing till beneath the ice. In other areas, especially where the shelf is broad and gently sloping ice margins, may stabilize inland from the shelf break, leaving parts of the outer shelf under floating ice or seasonal sea ice rather than thick grounded ice sheets. Where grounded ice is present, it can produce streamlined landforms in soft sediments, sculpt bedrock highs, and leave behind irregular fields of till and morainic ridges when it retreats. These features later become buried beneath marine deposits as transgressions flood formerly glaciated shelves. In locations where the ice front remains close to the shelf, large volumes of sediment are delivered to the continental slope and rise by subglacial meltwater plumes and debris-laden flows. These processes generate thick accumulations of glaciogenic material in submarine fans and apron systems beyond the shelf. Farther offshore, in deeper ocean basins that surround Kenorland, cold surface waters and extensive sea ice dominate the uppermost layer of the water column during peak glacial conditions. Sea ice forms seasonally at first and may become perennial over wide areas as climate cools. In regions where sea ice is widespread but not continuous leads, and polynyas, which are open water patches within the ice, cover allow exchange of heat and moisture between ocean and atmosphere. These openings can influence local weather and support limited surface gas exchange and biological activity. Where sea ice becomes thicker and more persistent, it insulates the ocean from the atmosphere and reduces the direct influence of winds on the surface. Beneath the ice, cold, relatively fresh surface waters overlie denser, more saline layers. When sea ice forms, salts are rejected from the crystallizing ice and increase the salinity of nearby seawater, promoting the formation of dense brines that sink and contribute to deep water masses. This process helps drive vertical circulation in the ocean, with consequences for the distribution of oxygen, nutrients and chemical species. The broader circulation around Kenorland's margins depends on basin geometry and on the locations of constricted seaways. Where narrow connections between major ocean basins exist, currents can be focused and strengthened, funneling water masses and icebergs through specific passages. Along open continental margins, wind-driven currents may flow parallel to the coast, transporting water and sea ice along the flanks of the supercontinent. Upwelling where deeper waters rise to the surface can occur along some sectors, especially where wind patterns push surface waters offshore. In an ocean that remains largely anoxic at depth, such upwelling brings iron-rich and chemically reduced waters toward the surface, where they can interact with any available oxygen in the upper layers. These interactions contribute to the precipitation of iron-bearing minerals and to the chemical stratification of the water column. At the seafloor on shelves and slopes around Kenorland, sedimentation under glacial influence produces a variety of facies. Close to marine terminating ice fronts, glaciogenic diamictites may accumulate. A diamictite is a poorly sorted sedimentary rock containing a mixture of grain sizes from clay to boulders, often interpreted in this context as lithified equivalents of glacial or glaciomarine deposits. Such diamictites can form from the direct settling of debris from floating ice, from the dumping of subglacial till into deep water as ice reaches the shelf edge and destabilizes, or from the action of debris flows that remobilize sediments down the slope. In quieter parts of the shelf and in deeper basins, fine-grained muds and silts settle from suspension, sometimes interrupted by dropstones where ice-rafted clasts pierce the lamination. The presence of isolated larger stones embedded in finer sediments together with other lines of evidence supports interpretation of some paleoproterozoic units as glaciomarine. Proglacial marine environments at the ends of major fjord systems add further complexity. Meltwater that emerges from the base of marine terminating glaciers forms buoyant sediment-laden plumes that rise along the ice front and spread under the surface. These plumes can carry fine material far from the ice margin and drop coarser fragments more quickly. Seasonal variations in meltwater discharge may produce layering in the sediments that records annual or longer-term fluctuations, although post-depositional processes in paleoproterozoic rocks often blur these patterns. Where fjords connect to broader shelves, their over-deepened basins can serve as traps for thick accumulations of mud, sands, and ice-rafted debris. The morphology of these basins, shaped by earlier glacial erosion, influences the thickness and distribution of sedimentary packages and can later focus tectonic deformation. Not all Kenorland margins experience the same intensity of glaciation at the same time. Paleomagnetic and stratigraphic data suggest that some cratonic edges and their adjacent basins host multiple glacial units, separated by non-glacial intervals, while others have thinner or more sporadic glacial records. Margins at higher paleolatitudes are more likely to support long-lived ice shelves and sea ice, whereas those closer to lower latitudes may oscillate between ice-influenced and more open marine conditions as climate varies. In addition, the tectonic character of the margin matters. Active margins near subduction zones may be uplifted steep and subject to intense erosion and rapid sediment delivery, while passive margins may be lower, broader, and covered by more gradually accumulated shelf sequences. These differences are reflected in the thickness composition and structures of paleoproterozoic strata, preserved in different cratonic successions. In the cold surrounding oceans, the interplay between sea ice cover surface water properties and deeper noxic layers continues to shape the chemical environment. Density-driven circulation carries cold saline waters from high-latitude formation regions into the deep ocean, while return flows bring deeper waters back toward the surface in other areas. Where upwelling intersects continental shelves and slopes, it can influence both biological productivity and mineral precipitation. In an ocean with evolving oxygen levels, zones of partial oxidation may develop near shelves and in restricted basins, particularly where mixing is strong or where local oxygen production by microbial communities is significant. These zones can host distinctive chemical sedimentation, including iron-rich layers and other precipitates that form when reduced species meet oxidizing conditions. At the same time, organic matter produced in surface waters sinks and decomposes, consuming oxygen and maintaining or re-establishing anoxic conditions at depth. The margins and cold oceans around Kenorland thus form a dynamic interface where ice water and rock meet. Marine terminating ice sheets deliver sediment and ice-rafted debris to continental shelves and deeper basins. Sea ice regulates exchanges between ocean and atmosphere and helps drive circulation through brine formation. Currents and density contrast distribute water masses and shape the redox structure of the ocean. Sedimentation on shelves, slopes and in glaciated basins records the passage of ice and the chemical state of the sea. The resulting bodies of rock, now preserved as deformed and metamorphosed paleo-proterozoic successions on several cratons, capture regional scale patterns of glaciation and marine conditions along the former edges of Kenorland, complementing the records from its interior ice-covered plateaus and basins. At the smallest scale, the record of Kenorland's glaciated world is preserved in individual sedimentary basins, where layers of mud, sand, gravel and chemically precipitated minerals accumulate in quiet water and on gently sloping surfaces. These basins occur on the interiors of cratons along rifted margins and in subsiding regions at the edges of mountain belts. Each basin has its own geometry, water depth and connection to the open ocean, and each responds in a slightly different way to changes in ice cover, sea level and local chemistry. During glacial intervals, many of these basins receive direct input from ice-related processes. In shallow marine or lacustrine settings near ice margins, diamictites accumulate when debris-laden ice melts and releases its load. A diamictite is a poorly sorted sedimentary rock containing a wide range of grain sizes from fine mud to large clasts. In this context, it often forms from the settling of material dropped from floating ice or from the deposition of debris flows that originate at ice fronts. Within otherwise fine-grained successions, isolated larger stones known as drop stones appear embedded in thinly laminated muds and silts. These clasts fall from melting icebergs or lake ice into the soft sediment below, deforming the laminae and leaving a local disturbance. The presence of such drop stones in paleoproterozoic strata is an important small-scale indicator of the former presence of floating ice in water bodies attached to Kenorland or its fragments. In some basins, rhythmic layering develops as sediment supply, and water conditions vary through time. Thin couplets of silt and clay may record seasonal or longer period cycles in meltwater discharge with coarser material deposited during higher energy phases and finer particles settling during quieter intervals. When preserved, these structures offer a detailed archive of changes in inflow temperature and ice margin position. However, in many Kenorland age units later, burial deformation and metamorphism blur or erase such fine details, leaving only the broader alternation of coarser and finer beds. Even so, the overall architecture of the sequence with stacked diamictites, laminated mudstones, sandstones and occasional conglomerates gives clues about the relative importance of glacial, fluvial and marine processes through time. Local basins also host chemical sediments that record the interaction between ocean chemistry, basin restriction and evolving redox conditions. In some settings, banded iron formations occur in association with or above glacial units. A banded iron formation is a layered chemical sediment in which iron-rich bands alternate with silica. Rich bands formed when dissolved iron in the ocean is oxidized and precipitates as solid minerals. In the context of Kenorland, such formations can appear before, during or after major glacial intervals depending on how circulation and oxygen supply evolve. Their presence in a basin indicates that at least part of the water column holds enough dissolved iron and that conditions periodically allow oxidation, whether through contact with oxygenated surface waters or through other chemical reactions. The thickness, layering style and associated minerals within these iron formations provide information about the duration and intensity of iron deposition and about the balance between reduced and oxidized states in the basin. In other basins, carbonate rocks and other chemical precipitates form when dissolved ions in the water reach saturation. These carbonates can occur both in glaciogenic successions and in intervals between glacial units. Their isotopic compositions and textures reflect the carbon cycle and the degree of mixing with open ocean waters. In some Paleoproterozoic sequences, carbonate units overlying glacial diamictites have been interpreted as deposits that form when oceans adjust from cold, possibly ice-influenced states to warmer, more open water conditions. The exact mechanisms behind these transitions and their timing relative to global glaciation are still under study, but at the scale of individual basins they mark significant shifts in water chemistry and climate. Within these sedimentary and chemical frameworks, microbial life occupies small but persistent niches. There are no land plants or animals at this time. Life is dominated by microbial communities in marine lacustrine and subglacial environments. On shallow shelves and in coastal basins along Kenorland's margins, microbial mats develop on tidal flats and in very shallow waters. These mats trap and bind sediment grains, building stromatolitic structures that grow upward as layers of microbes and trapped particles accumulate. Stromatolites preserved as layered domes. Columns or sheets in carbonate and siliciclastic successions reflect local conditions of light water depth and sediment supply. Their distribution through time in Kenorland age rocks highlights intervals and regions where shallow, relatively stable surfaces exist despite broader glacial activity. In deeper or more restricted basins, microbial life shapes chemical cycles in less visible ways. In oxygenated surface layers, photosynthetic microbes fix carbon, and in the case of oxygenic photosynthesis, release oxygen into the water. Below in anoxic deeper waters and sediments, other microbes drive processes such as sulfate reduction, methanogenesis, and ion reduction, transforming sulfate into sulfide-producing methane and converting iron between different oxidation states. These reactions influence the composition of pore waters and the types of minerals that precipitate within sediments. As organic matter is buried, its partial preservation contributes to long-term carbon storage, while its decomposition consumes oxidants and helps maintain or restore anoxic conditions at depth. Isotopic variations in carbon and sulfur within these rocks record the integrated effects of microbial metabolisms and global reservoirs. For example, the ratio of light to heavy carbon isotopes in carbonates and organic matter reflects the balance between carbon burial and recycling, while sulfur isotopes in sulfides and sulfates reflect the pathways and extent of microbial sulfate reduction and the composition of the global sulfate pool. In Kenorland age basins, such isotopic signatures vary across glacial and interglacial intervals, indicating that local environments respond to changes in global redox conditions and to the reorganization of the carbon and sulfur cycles during the Great Oxidation event and associated transitions. At the bed scale, the interplay of physical and chemical processes produces characteristic features. Thin laminae of fine sediment interrupted by isolated pebbles mark episodes of quiet deposition, punctuated by iceberg passage. Graded beds of sand and silt record pulses of higher energy, flow perhaps tied to meltwater floods or storms. Iron-rich layers, sometimes with microcrystalline textures, indicate times when oxidized iron minerals form from dissolved iron carried into the basin. Carbonate lenses and nodules reflect local saturation states and diagenetic changes as pore waters evolve during burial. Deformation structures such as soft sediment, folds and lode casts show that some layers are still unconsolidated when overloaded by rapid deposition, possibly during outburst floods or sudden changes in ice margin position. At the margin between glacial and non-glacial deposition, mixed facies appear. In some sequences, glacial diamictites grade upward into more typical marine sandstones and shales, suggesting that ice retreats from a basin and that open water conditions return. In others, non-glacial deposits are abruptly overlain by glacial units, marking the advance of ice into previously ice-free regions. Repetition of such transitions within a basin reveals that ice does not simply appear and vanish once, but may advance and retreat multiple times over the duration of the Paleoproterozoic glaciations. The thickness and number of these cycles differ from basin to basin, reflecting local tectonic subsidence rates, proximity to ice sources, and global climate variations. Many of these basins lie along zones that later become sites of rifting or renewed orogeny. As Kenorland breaks apart and its fragments participate in new tectonic cycles, these sedimentary packages are buried deeper, heated, and deformed. Metamorphism can alter original minerals, transform sediments into schists and gneisses, and overprint textures. Even so, some primary features such as dropstones, laminations, and iron-rich bands survive in recognizable form. They provide the tangible local evidence that glacial ice, cold oceans, and evolving redox conditions once prevailed in the environments attached to Kenorland. By comparing many such basin-scale records across now-distant cratons, researchers reconstruct the broader pattern of Paleoproterozoic glaciation ocean chemistry and atmospheric change. At their core, however, these reconstructions rest upon small exposures of rock in ancient valley shelves and basins, where layer by layer mud, sand, pebbles, and chemical precipitates quietly record the presence of ice water and microbial life in the world of Kenorland.